Hello everyone. In this lecture, I will discuss ADC programs. There are two programs which we will discuss. The first program will be on using ADC channel 5 and whatever with the analog input over the ADC channel 5 that we will display over LCD screen. Then in the next program, I will discuss how to use the modules ADC module in burst mode. For that we will use both ADC channel 4 and ADC channel 5 and will give inputs to both the channel and whatever be the output difference in the channel, the absolute output difference in terms of the digital voltage that we will display over the LCD screen. So one program we will discuss on the line of software controlled mode and another program will be on burst control. These are some of the steps which are right in front of you. So these steps will follow in both the program. So first and the foremost thing while using any other peripheral is selecting the function using pin select register. So here we will use AD05 and AD04. In one program AD05 we can use any one of these two in the first program, the software control. In our situation we will use AD05, that's the fifth channel, and that corresponds to pin number 31 of first port. So port P1.31 corresponds to AD05 and pin 1.30 corresponds to AD04. So corresponding to those channels, we have to first select the corresponding pin and the port using the pin select register. So here as you can see, so AD5 P1.31 and the function select would be 3. So over the pin 30 and 31 and pin select 3 register, we will write 1 over 30 and 31 pin. Likewise, if we have to use AD4 channel 4, then the corresponding port and pin would be P1.30 and the function select here also it is 3 and to realize this function over the pin 30th pin, we have to write 1 over the pin select bit positions 28 and 29 in pin select 3 register. So that's all about configuring the pin so that later on those pins would start functioning as ADC pins instead of GPIO pins. That is the first important thing where from we will start our program. Then if we are adjusting our clock, then we will adjust our clock and enable the clock using PCLK select 0 register and the corresponding bits already we have discussed in ADC theory lecture that the pin PCLK select 0 register and its 24th and 25th bits corresponds for selecting the proper relationship between the PCLK, the peripheral clock in respect to core clock. So there were 4 possibilities. Out of those 4 possibilities, if one we have to subscribe and one relationship in between PCLK and CCLK we have to give, then on the 24th and 25th position, the bit position, we have to give the right value, the corresponding right value. Then there is an ADCR, the ADC control register, that is the main register. The ADC control register already we have discussed in ADC theory lecture. And there in that ADC control register, we have to select um, the right channel over which ADC will then start converted the analog to digital value. And then to power up the ADC module, there is a bit over the 21st module. If we have to work in bus control mode, the bit position 16th corresponds for selecting the ADC module in burst mode. And likewise, there are several other controlling features which we can control, which we can configure through ADCR register. So these are all 3, 4, and 5. So these are all corresponding to selecting the proper bits and then configuring those bits for controlling the ADC module. Then once we have configured the ADC module through ADCR register, then we will wait till the conversion happens. Once the conversion will happen, then we will go to either the global data register, or if there are several other specific to channels, the data register, where also from we can get the converted value, the 12-bit value. So that 12-bit value we will then read. We can later on convert also. That conversion also I have discussed in my previous lecture, that how to convert the 12-bit digital value after conversion, because the ADC module in our situation will use 12-bit successive approximation, and so it requires 12-bit register for converting analog value to digital value. So once you have with the 12-bit value, how will you then convert into its digital equivalent voltage value? So that conversion we have discussed in the last lecture. So you can consult, you can refer to that last lecture, that how to convert these 12 bits into its equivalent digital output voltage value. Once you get the value, then you can display it over 7-segment, you can display it over LCD, you can use it for another reason. So that's all about, that is in brief, all about how we will proceed to uh, while writing the program regarding ADC modules. Now we'll straightway go to our first program, and this program is corresponding to software control mode. And in this in this program, the idea is whatever be the input analog voltage value on the channel 5, that value first will convert into its digital equivalent using the PC, and that converted value then later on we will display on LCD. So LCD will use, so LCD program we will use straightway as it is. I will not discuss the LCD program here. I will just focus only on the ADC part in this program. So this is the reference voltage. So for successive approximation algorithm, there it needs a reference voltage, and that reference voltage in our situation corresponding to 1768 is 3.3 voltage, and its equivalent digital 12-bit output is 0x FFL. So if there is a 3.3 voltage, its equivalent 12-bit equivalent digital output is 0xFF. So this we will use. So these things we require for converting the converted to 12-bit value into its equivalent voltage value. So that's why these two variables we require, and we have defined these things here. Now in the main program, So this is the temporary, this variable will hold the temporary voltage value, and these two are character arrays that we will use for converting whatever be the value, the converted digital value into string, because that later on we will send to LCD for displaying purpose. So this is for that reason. And these are the two messages, the character arrays that we will, so these two strings we will display on our LCD. So analog input we will display on the first line, then on the next line from the 0th character position we will write ADC output. So analog input, so whatever be the analog input, that we will write later on in front of this, and its corresponding output value, the ADC output value, that we will write uh, in the next line after ADC output over LCD character display unit. Now here we are using channel number 5. Channel number 5 is already I have disclosed that channel number 5 would require pin which is P1.31. So that for that reason we are using pin select 3 for selecting the proper function. Otherwise, if you will not select it, that pin would go for GPIO. But here we want to change it from GPIO to function number 3 that corresponds to ADC function. Then P1.31 after this line will start functioning as ADC pin. Now the configuration is over. Pin configuration is over. Here we are configuring the power. So in the power configuration register, so that is the part of system configuration, LPCSC system configuration. So there is a power configuration register already. We have discussed about the power configuration register. This is the register through which you can power up the peripheral units. So here the 12th bit corresponds to ADC module. If you have to power up ADC module, then 12th bit should be 1. So that's why 1 we will shift 12 times and over it with power configuration. So that will power up or enable the peripheral ADC. So these commands are for displaying analog input. I will not go into the detail of what exactly these lines are doing, but this is 0x80 is a command for going to the first line, and it is 0, so going to the first line and on the 0th character position and execute this, and after a certain delay write this message, put this message over the first line from the 0th position. So that's all we're doing in these 4 lines. Exactly on the same notion. So these lines are also for displaying the ADC output. So this thing will be then written over the second line from the 0th position. So 0xc and 0 stands for from the 0th position. So cursor will go to the second line and it will start blinking over the 0th position, and whatever later on you will write will come over the LCD display from the 0th position. So after these lines, the output would be over the display unit, LCD display unit. Analog input would be on the first line and ADC output would be on the second line. Now our programs start, which is the core of ADC program. So here in the infinite while loop, first we will configure our controlling register. The controlling register here is ADCR, analog to digital control register, ADC control register. Here in the control register, we are using the software control mode. Only one channel would be there. So the 5th channel we are using. So this thing corresponds to selecting the 5th channel. So in the power in the ADCR register, initial 8 bits corresponds to 8 corresponding to selecting channels. And here our idea is to select the fifth channel. So we will select the fifth channel here. Then 21st position corresponds to power up the device, power up the module once again. So already there is a in power configuration. First you have to write 1 over the bit position 12. Once again there is a check on the power, it is a power down bit. That power down bit you have to make 1. So once again giving it to the power, so it's an additional check on the power. So this is for that purpose. And now, in my last lecture, I discussed that if you have to start it, so until and unless you start the ADC module, it will not start converting it. To start converting, is a start bit 24, 25, and 26. So these bit should have the value 1. So 24th bit, because the value 1 means 24th bit should be 1. So 0 on the 26th bit, 0 on the following adjacent 25th bit, and on the 24th bit the value should be 1. So here exactly the same thing we are doing. So we are shifting it by 24th 1, and then we are ORing it with whatever the content of ADC at that time. So in this way, what you have done, you have selected the fifth channel. Here, power up the device. Here we are not using the burst mode, so 16-bit we will not touch. 16-bit should be 0, and 21st bit should be 1 for power up the device, and the start bit should be 1 in 24, 25th, and 26. So that equivalent decimal value should be 1. So that means 24th bit should be 1. So that's how we have configured it. Once you have configured it and you have even given the direction for starting it, then we will wait till the ADC module execute, and till the time it isn't convert the value. So till that time we will wait. So how we are waiting and how we will check it that it has been converted through the corresponding register, data register. So here directly we are using the ADDR5 register. ADDR5 register. Here in ADDR5 register, from 4th bit till 5th bit, we'll get the 12-bit approximate equivalent digital output that we will use later on for converting into its digital equivalent voltage output. And the 31st bit, is for mentioning that value has been converted. That is the done bit. So that done bit we will keep on checking. So if you will see in the calculator, so this is the hexadecimal value. So this value you can see here 8000. So if you will convert this into say 8000 into its equivalent binary value, then over the 31st bit position, if you will start it from the 0th position, so this 31st position is 1. And our idea is to actually end it with ADDR5. If in ADDR5 also the done bit is 1, then it will give you the 1, and then you will come out of this LPC. Otherwise, because not is there, you will always keep on working inside the while loop until and unless the 31st bit in the ADDR5 would become 1. Once it will become 1, that ensure that conversion has taken place. Now, once conversion has taken place, our next goal is that we want to read the value, the converted value. And the converted value lies over the bit location 4 till 50. So now our idea is to actually bring back this value, convert this value, and take this value in some other variable. So see ADC ADC temp, and in ADC temp directly whatever be the 32 bits in ADDR5, we are actually taking an ADC temp, and then in ADC temp we are shifting ADC temp by 4, because from 4th location till 15th location the value exist. So now whatever was there on the fourth would then reach over the zeroth location, and then we will end it with the FFF. So initial 12 bits are 1. So whatever be the value comes, that comes in ADC temp. So this is the value which reside after conversion over the bit location 4 till 15. So that thing uh, is now in our ADC tab. So this is the 12-bit value. So once you are with the 12-bit converted value, this thing then you can convert to using this. So this is the formula. In my last lecture, I discussed about this formula, that how you will convert the 12-bit. It's simple ratio and proportion. So in this way, these 12 bits ADC value, which is over the ADDR5 bit position 4 to 15, that we have converted and we have stored in INVTG, this variable, because now this variable we have to provide to our LCD display unit. So we require one string out of this. So whatever be the value. So this is these two lines. So this is the converted value. That thing we are storing in VTJ. Already I have discussed that VTG1 character array. So whatever be the converted value, the correct we are storing in VTG, and uh, so using sprintf, so convert the reading into string to display on LCD. So in this format, we have stored it in the variable VTG. That variable and whatever be the converted value, ADC temporary value, whatever be the converted value. And so initially, this is ADC temp. ADC temp contains the 12-bit value, the 12-bit value. Understand this 12-bit value. So we have to display the voltage value also, the converted voltage value, as well as the 12-bit value in decimal format we will store. So ADC temp and its decimal equivalent, decimal value. After certain delay, so these are the lines responsible for writing the converted analog value as well as its digital 12-bit value over to the display unit, LCD display unit. Already we have written using these lines. Using these lines, we have written analog input and ADC output over the lines. So now we don't want to overwrite over these already written value. That's why this time the command is 0x89. So 0x8 will take you to the first line. Now the cursor will blink and cursor will position itself on the 9th character position instead of the 0. Whereas you can see the difference here, it is 0. So that's the only difference. Otherwise, the subsequent lines are same. Initially, we were writing some other stuff, and here we are writing the converted value. That's all. Likewise, in the next line, when you have to come 0xc will take you to the next line, and this 8 uh, uh, is different from what was there initially 0, because whatever you will write here will take you to that character position on that line. So 0xc will take you to the second line, and 8 will take you to the 8th character position. From there, you will start writing it. And once again, in these lines, whatever is there in VTG array and decimal value, you are making it 0. So once again, converting the new value. That's all. So this is all about the software controlled mode, in which whatever was there on the channel 5, that later on we have converted using ADC module, and after conversion whatever was the converted value written over the bit position in ADDR5 register from 4th bit location to 15th bit location, that we have written. So it is a simple program, simple enough to understand. And so now in the next program we will discuss about burst controlled mode, how different channels we will use. So the maximum possibility through our kit is we can at most use both the channels. So the channels available are 5 and 4, and 5 corresponds to pin 1.31, 4 corresponds to pin 1.30th. So how to configure it? If we have to use both the channels, then we have to obviously configure both the pins as ADC pins instead of GPIO pins. So once again we will see how to configure. AD4 also we have to use. So in pin select 3 register, 28 and 29 bit location should also carry the function 3. So 1 we will write over that. Likewise, in our previous program, we have seen corresponding to AD5. Once again, if we have to use it, then 30 and 31 bit should be 1. That also corresponds to the function select 3. So that is all about configuring the pin. So then subsequently in ADCR register, that how to configure and control the ADC module through ADCR register. So here we are using both pins and both channels, AD4 and AD5. So 4th bit and the 5th bit of ADCR register should be 1. And because here there is no concept of start, so start bit 24, 25 and 26 should be 0, 0, 0, because ADC would internally control uh, when to start and not to start, which module to work with, which module to not work with. So internally that all churning would happen. So for that to realize through the controlling register, the 16th bit should be 1, because 16th bit corresponds to burst mode. And obviously you have to power up the device, you have to power up the ADC module. So first you have to configure the power configuration register, and its 12th bit should be 1. Likewise, the next check also through the ADCR register, that is the 25th PDN bit, that is the power down bit, that also you have to make it 1. Then only it will start functioning. So that is all about, we are not touching the clock. Otherwise, if you have to adjust the clock also, so first adjustment would be using the PCLK select 0 register, and its 24th and 25th bit you have to adjust accordingly, the way you want to set the relationship in between PCLK clock and the core clock. That is one thing. Further, if you want to divide your peripheral clock, then there is a further division possible, there's a further adjustment possible, that is through clock division. And that bit is from 8 to 15 in the ADCR register, but that we will not touch. Whatever is internally set in our kit, we will abide by that regulation. And let's see with the program. ADC burst mode. So here also let me briefly discuss this program, that this program is all about what. In this program, we will use both the channels, 4 and 5th channel, and we will give some input to those channels, whatever be the absolute voltage difference over these two channels. So channel 1 individually we will convert, we'll get its converted value, that we will keep aside. Likewise, for the next channel, we will once again convert whatever be the value comes after conversion, we will take the absolute difference. That absolute difference, then we will take to our LCD display and display over it. That's the simple program. So through this line, we are enabling the ADC peripheral through power configuration. Now, using this line, we are configuring port number 1, pin number 30, and pin number 31 as ADC pins. So 0xF means 111 because 28, 29 bit should be 11, and 30 and 39 bit should be 11. So from 28 till 31, if everything will be 1, so it is 0x F means 1111, and you will left to shift it by 28 times. So over the bit locations 28, 29, 30, and 31, it would be 111 after the execution of this line. So this is all about configuration of pins. In the next line, we are configuring ADCR register, that is the control register. And because we are using the 4th and 5th pin, so 4th and 5th pin bit position should be 1. 16th should be 1. 16 is corresponding to burst mode, and 21st bit is for power up the device, that is PDN bit, that should also be 1. Now here, because we are using both channels, and internally the conversion will happen, and once conversion will happen, obviously the done bit would be 1, but there may be a possibility of overrunning. The overrunning means that once you write the value over the data register, it may be possible that without reading it, once again the conversion would take place over the same channel, and there would be overwriting over the previously written value prior to its reading. That is called overrunning. That may be possible. To avoid that thing, we will use interrupt. So as soon as done bit would be 1, it would trigger the event, and interrupt will then handle it. So we will handle our conversion once the conversion would take place. That conversion once take place, then we will handle it through ADC handler, interrupt handler. How we will handle it, we will see later on. First, see that how to enable the interrupts. So there is an ADC interrupt enabler. This register, initial 8 bits are being used in the ADC interrupt enable register. So here we want to associate it with the channel 4th and channel 5. So its 4th bit and the 5th bit should be 1. That means the moment the done bit corresponding to ADDR4 and ADDR5 would be 1, that would trigger an interrupt, it would trigger an event interrupt, and then our handler will handle it. So this is something which we are writing. So nothing we are writing what is the ADC value. So that we are displaying whatever is the converted means the difference. So ADC value, if we have to write ADC value over the display unit, then these lines are sufficient to do that. Here in this line, we are enabling the interrupt. This line is essential because if we will not enable the interrupt, even after enabling it through AD interrupt enable register, you have to enable it through NVIC enable function. So that would enable the interrupt, then your code, your system would look for that sort of an event, and once that event happens, then it would trigger the ADC IRQ handler. Now, what are we doing in the interrupt handler? Nothing we are doing. The moment anything happened, the done bit is 1. We will check whether the 4th been converted or 5th been converted. the fifth channel, the corresponding input signal over the fourth being converted, or the input signal over the fifth channel would be conducted or not. So for that, we will check the AD stat. So AD stat is also one of the mirror image register, which will hold the mirror image of the done bit corresponding to all the channel registers, as well as their overrun bit. And here we are only interested in the done bit. So initial 8 bits corresponds to the done bit. So here we are interested in the fourth and fifth bit. So 3 3 means 3 times, 3 means 1 1. So 1 1 we will left shift 4 times, and AD stat. So fourth and 5, because our interest in figuring out whether fourth been done or fifth been done or both been done. So then X will hold the value corresponding to the bit location over the AD stat, or in other words, we could put in that way that X will hold the done bit corresponding to fourth channel and the fifth channel. Now, the moment you have this information, then here in this if and else conditions, we are checking for individuals channel, whether it is for fourth and fifth. So if it is for fourth, then from the ADDR4 register, whatever be the value corresponding to the bit location 4 to 15th, that 12-bit ADC value we are figuring out, and that we are storing in T1. Likewise for fifth, we are storing in T2. Once we have both the values T1 and T2, we are converting it using the same converted formula, simple ratio and proportion. Once you have both the output values in voltage, then we are storing their absolute difference. Then whatever be the result, that out of that result we are making a string, and that string we are displaying over to the LCD. So that is the program. So in software control mode, we didn't handle it through interrupt, though we could have handled it through interrupt as well, but there was only one channel, so the chances of overwriting the stuff was not so much. But here, because both channels were providing input to the system, and the system was handling it through round robin way, so it may be a possibility of overwriting the stuff in several data registers, particularly in ADGDR, that is the global data registers. To handle that thing, we did it using the interrupt handler, and that is all about ADC. In next lecture, we may discuss some other peripherals. Till then, goodbye.